So I'm going to first start with a PowerPoint presentation, just because it's a bit easier to go through the product. So this is called the Industrial Mechatronic Drives Unit. It's one of our, and we use the acronym IMDU or IMDU. I'll use both during the presentation, so get familiar with the lingo. But I'll go through the product features, the system overview, that being like the different components being involved, and then we're gonna go through a cool braking demo that I got rigged up here. So having said that, I'll just get started. So the IMDU base unit features. So let's go through this first. Now there's two actuated servo drives. So those two shafts that are shown here and here, those are driven using servo motors. So the motor is connected at the bottom here. So the motors are connected via a belt drive. So all the shafts are belt drive driven through the motors, but there's also a gear train, 3-to-1 gear train. So that enables you to get really high torques at these outputs. So the motor's right here. Well, it's inside here, it's belt driven, and it drives both these actuators, these shafts. And as you can see, you can mount different things like different inertial loads and all that, which I'll get to. The amplifiers are integrated inside the system, so they are internal. They're current control. They have overheat protection, and they're all embedded inside. So you don't need a separate or external amplifier to drive these motors. There's two unactuated shafts, so this one and this one here. So these are just shafts that are not driven by the motor, but they are measured. And in fact, all the shafts are being measured using high resolution encoders. So you can use that, of course, to measure the position of each shaft. And through software, you can compute the velocity if you want to do rate control, for example. On the picture, and as I'm showing here, we have some inertial loads that you can mount. So two inertial loads are offered with the system, and each one comes with four weights, 4 brass weights, and you can vary the position of each weight. Right here, I got 2 on this disc, and that's shown in the image in the bottom left and the bottom right, and in the top left, you see here you can add you could put the four on. So this allows you to change the inertia of the disc load easily. Rubber belts, so you can connect these two systems together using the two rubber belts that we have. And finally, there's a belt tensioner. So the belt tensioner shown here, so you can use this to add tension to the belts depending on your configuration. Lastly, there's an emergency stop switch that's also included. So you have to connect this to the system in order to be able to drive the system. And and you can just like clamp down on that system, and it'll shut down the current going to the motors. Okay, pulleys and belts that are offered with the system. We have a total of 5 pulleys. So with some different, so 48 tooth right down to 20 tooth pulleys. 2 belts, 103, 132 tooth belts offered here, as shown here. Then got one connected. So this allows you to set up various configurations. I have one configuration that you see on the webcam that's connecting motor 0 with the passive shaft number 1. You could also, as shown in my PowerPoint slide on the right there, you could connect both motors together and have one feed a disturbance to the other one, for example. That's one of the labs we supply. So there's many variations with this, and that's one of the key advantages of the product, are the number of configurations that you can set up. On top of that, we also supply what's called a brake drum and friction unit. So that's shown on the left, and I'm pointing it out right here. Camera. So with this, so you can apply this and connect it, so you can mount that on the base of the IMDU, and this applies a direct friction on the load shaft, right? So instead of simulating the friction that goes typically directly into the input, and it's usually easily compensated for, you can add an actual like stiction to the load shaft using this. And from that, you can use friction identification and compensation schemes. Backlash unit. So the backlash unit, so gear backlash is a phenomenon, a nonlinear phenomenon that's discontinuous. So when you have some play between the teeth of two gears together, then you have backlash, right? So if you want to emulate that, you can actually vary the amount of backlash and stuff like that with this unit. Here's an example of how you would rig up a backlash, right? So the backlash unit would be on the on the right there, and you would drive it on the left spindle, and then using a belt tensioner to add some tension to the belt. You would add, again, you could vary the backlash between like almost 120 degrees, right? So you can vary plus or minus 60 degrees the amount of backlash you want acting on the motor. So again, so you can use this to do some identification protocols, or even to compensate for that, or showing the difference of what backlash does when you don't model it to your controller. So there's many possibilities. So these again are all offered with the standard base unit. So the 5 pulleys, 2 belts, 2 inertial discs with the weights, the friction unit or the brake unit, and this backlash unit. That's all offered with the standard system. Documentation. The IMDU is fully documented. We have a user manual that details the different hardware specifications of the system and how to set up the system, how to connect it together. We also have a laboratory guide. So the laboratory guide will show you how to run through the controller examples that we supply, as well as some simple modeling and the control design we will outline the control design that's used in the examples. So some background theory in there. So I'll show an image there on the right of one of the pages. Example labs. We have 4 example labs. So actually dual drive position control. It's not actually single drive. So you can drive both spindles at the same time simultaneously from a single Slimlink model using our Quark software. I'll get into that a little bit later. Same with speed, so you can control the rate. The disturbance rejection, which I showed earlier, so when you connect motor 0 and motor 1 together, motor 1 feeding a disturbance to motor 0, and then you would compensate for that. And even haptic knobs, so we have a little cool little haptic example on there, so where you would change like the stiffness and the tension of the dial and stuff. And there's an image shown there, so you would feel the difference as you adjust the different settings of your haptic, right? So this is basically like force feedback. And there was actually a paper written recently that was submitted to the Haptic Symposium based on the IMDU. So that was very recent, this year, I believe. So the reference will be posted on Quanser.com under research papers if you're more interested in that. So you can find the reference on our website. So applications, basically this has practical relevance to any kind of multi-servo system that you see in industry, for example, and just because of the sheer number of configurations that you can set up on this, you can emulate, for example, like a simple vehicle transmission, kind of a proof of concept. It's also used again in academic research a lot, to develop advanced modeling and control algorithms, or like the one I mentioned, right, the haptic example. So on top of that, I'm going to go through 2 optional modules or add-on modules. So these are available. They're purchased separately, and you can mount these on the IMDU. So the first one is the web winding module. So the web winding module is shown on the image here. So you have 2 paper rolls, and you would be controlling the rate of the paper. The other thing you can control is the tension of the paper. So you have an arm there, basically, that adjusts the tension of the paper, or how stiff it is, right? So this could be actually perceived as it's basically a multivariable controller. And this whole system, simulates basically like you could like a pulp and paper plant, right? Like an example system in a pulp and paper plant. So it's an example of a more advanced system that you can put together on the IMDU using this add-on module. And I show a diagram here on the right that kind of that shows you the workings of how each component works together. I'll show you a short video of how it looks like when it's running. So this is it starting up. So we're adding tension here. The arm moves, and then we start controlling the rate of the paper. So right now it's just moving at a slow rate, and then you can see it's going back and forth. You have to go back and forth, otherwise the paper runs out after a while from one of the spools. So, and then it goes back. So that's just a short video, demonstrating the web winding module. Another module they have also available for a separate purchase is the torsion module. So the torsion module, at the base, we have the IMDU, right? So this is one of the actuated shafts, right? So it's driven by the motor. Then we have some torsional couplings. So we have two torsional members, one on the motor side and one on the top there. So that adds the flexibility in the rotation. On the top, we have the load. So the load, of course, is unactuated, and you can mount the same inertial disc that I showed you before. And again, you can vary the weights that are on there. You can even connect different loads together on the top. So you can use the belts and basically the same kind of configurations you can do on the bottom that I described earlier, you can do on the top load. So you can make this as complicated as you want. Now, all these load shafts on the top ride on these ball bearing blocks at very low friction. Again, these are not motors. These are they're the ball bearing blocks, right, for the shafts to rotate. And again, all the shafts you see on top, all the 4 passive shafts are measured using high resolution encoders, the same ones that are used for the base unit. So in this system, you could have up to 8 measurements. You have 8 encoders available to you. The free body diagram is like this. So you would apply a current that goes through the amplifier, and that would be going through the motor drivetrain and actuate the motor shaft, and then that would move the torsion shaft. But of course, you have this flexibility in the middle there, right, introduced by the torsion module. So you could do experiments as highlighted on the right here. So you could do, for example, and this is one of the examples that we apply, a partial state feedback and full state feedback controller, all running from the same file. So in partial state feedback mode, you'd just be controlling the motor position, right? So you go back and forth in motor position, and then when you look at the position of the load shaft, you get very high vibrations at the load shaft, right, on the top there. And if you start using both encoder measurements, by both I mean the encoder measurement from the motor and the encoder measurement from the load shaft on the top of the torsion load shaft, then if you use both, then you have then you can start having a much better response, right? So now your load after your torsion starts to track your motor as desired, right? So you lose all those all that resonance and stuff. All right, so we're gonna start approaching for the demo here. So here's how the whole system works. So I want to just discuss the general system setup. So I got a computer. So you have a computer or laptop, and you run your controller on your laptop on your CPU. And then I have a USB-based data acquisition device. Today I'm using the Q8 USB. Our software supports many different data acquisition devices. You just have to make sure that it has up to 4 encoders if you want to measure all that simultaneously. So we're using a Quanser Q8 USB. It's an 8-channel USB-based DAC device. So that will supply the control signal that's computed on my control algorithm running on my PC. It computes a current. So the current is applied from the DAC to the amplifier inside the IMDU, and that drives the motor. And then you read your encoder measurements. So that's basically the cycle. That's the control loop from a practical point of view. As an option, and what we're going to do in the demo today, you can also drive visualization. So we have visualization capabilities in our software. So you can link this with the hardware and make it a bit more of a more interactive demonstration using this. Software options. So whether you're a MATLAB Simulink or LabVIEW user, we have a solution for you. I mean, we've had Quark for quite some time now. Quark is our software. It's a rapid controls prototyping software, and it's seamlessly integrated within the MATLAB Simulink environment. So it generates real-time code from a Simulink diagram. It has hardware blocks that enable you to talk to data acquisition devices, and it has other capabilities as well, like and I'll show you a couple of additional blocks it gives you to save you development time. So it's optimized for the modeling and control engineer, and it basically makes it easy for you to use hardware through that MATLAB Simulink environment if that is what you're used to. If you're a LabVIEW user, then we also have a solution for that. We have another rapid controls prototyping toolkit that works with LabVIEW, in particular with the control design and simulation module that they have. So this again will speed up your development. We have a number of blocks, number of VIs and stuff that will assist your control design. And through this RCP toolkit, you can also, for example, support the Q8 USB. So it has support of course, many National Instrument cards as well as many all our Quanser cards. All right, we are ready to start doing the demo. So before I give the demo, so I'm not going to go through the standard type of servo experiments that are offered with the IMDU. Like we've conducted a couple of webinars now with the Cube Servo and the SRVO2 that deal with like servo, standard servo, like modeling, position control, speed control, and those sort of experiments. Today, we'd like to focus on something a little bit more specific. So we're going to focus on a braking demo. And what I want to demonstrate is basically the wheel slippage when you're using like a normal braking system and when you're using anti-lock brake system or ABS. This is based on an example that we dug up from the MathWorks website. And it's an idealized model because you can measure slip. So of course it's not practical in that sense. You can't do that in an actual vehicle. But it's just a proof of concept. So, and the controller that they use and that we'll implement on the hardware is a bang-bang or an on-off controller. So again, a little bit of background here. Again, I'm doing this just because otherwise the demo won't make sense to you, especially if you're not familiar with braking demos and stuff. So the vehicle speed is going to be represented by as an angular velocity, and I'm going to show this a bit more thoroughly. So here's the linear vehicle speed, right? This is like your speed of your car that you feel with respect to the ground. But of course, on the IMDU, I want to simulate this on the IMDU. The vehicle speed is going to be this big metal disc that you see here. So this will be the vehicle speed, but it's represented as angular velocity. And you simply do that by dividing the linear speed of the car or the vehicle by its tire radius. The slip equation, so the amount the vehicle slips is right there. So there's the equation. So it's 1 minus the wheel angular velocity. So that's your tire on the pavement divided by the speed, the angular velocity of the car, shown by the denominator there. So that's the slip equation. But anyway, focus on the big picture, not the equations, but I think it's important to just highlight that. So again, I got the tire or wheel speed is going to be represented on the left. So this is what I'm being driven by the motor. On the right, it's again, that's the vehicle speed with respect to ground. That's what the user would feel, right? So the car speed. And again, it's represented as angular velocity because that's the only way I can do it. And now I'm going to be driving a visualization with this as well. So let's go through it. So now in terms of visualization, how does that work? You're going to see the following, right? So you're going to see the tire wheel speed in here, but that will also be represented on this visualization as follows, right? So you're going to see the tire spinning. So the tire that you see on the IMDU will drive the tire speed on the visualization. So they're all linked together, right? The visualization drives, the hardware drives the visualization. Then the vehicle speed with respect to ground, again, this will drive the visualization by, this will drive the car speed, right? So we take that angular rate of this big disc, we multiply it by the radius of the tire, that gives the linear velocity of the car, and that's what drives the visualization. So I hope that makes sense. And on that note, I think we're ready to go ahead. So I'm going to close this. I'll minimize my, I'm going to open up MATLAB. So here's the CIMIC model that we put together to demonstrate this. So let me just go through it a bit. So what we're going to do is how the demo works. I'm just going to turn on the IMDU on the back here. So we're going to take the first 6 seconds. The first 6 seconds, we bring the vehicle to initial speed of V0. So it's like 88 feet per second. About 6 kilometers an hour, something like that. So we bring the car to initial speed. This is all this does. And based on the linear speed of the car, we transform that and we give it, that's what drives the motor here, the tire that you see on your screen, right? So the desired speed of your car drives the tire. So that's it for that. So that drives the tire. And then this will naturally start spinning the vehicle. Both of those will be at the same rate, right? And then we calculate the slip. Again, that's idealized, right? You couldn't calculate the slip in a practical point of view, but we calculate the slip. So by reading the vehicle speed on shaft number 0, so reading the speed here, then we can calculate the slip and we feed that back. If you have ABS on, then you use the feedback. If you have it off, which I have it right now, then you don't use any feedback and it's just the slip is just direct, right? If I double click on the wheel speed with braking, this part again is from the CIMIC example. The bang bang controller is implemented using a sign block and Simulink. Then you have then hydraulic lag, brake pressure, force and torque. Those are all like actual vehicle like simplified, but they're all actual vehicle specs. Same with the tire and all that stuff. So I'm using a lot of actual like vehicle specifications, but once you compute the speeds and all that, it gets translated. The speeds are translated to the IMDU. So in order to run the hardware, there's some cork blocks in order to do that. So if I double click on the controller for the speed of the tire, I double click on here, you'll see I have a controller here. This controller is just a simple PD controller, but Cork has a PID controller block that makes it a bit easier. So does Simulink, but just saves you a bit of time. The Cork blocks that interface to the data acquisition device that talk to the hardware are as follows, right? So you have a hill write analog, a hill read analog to measure the current, and then hill read encoder to measure the position of this guy. In order to measure the speed, then we have a second order low pass filter, but it also outputs the derivative. So it's a filter derivative using this second order filter, and that's how we measure the speed of the tire. Pretty much the same deal for the vehicle. So we have a similar block using using a cork again to measure the speed of the vehicle. And then lastly, at the bottom here, that is the visualization. So as I said, so Quark has a menu. So once you install Quark, you get a menu like this. If you want more information, there is a webinar. There are different webinars on Quark that go through this a bit more thoroughly. So in order to generate the code, you go to the Quark menu and you select the build item, right? So this will generate the code, the real-time code from your assembly diagram. Okay, so it's been downloaded to my target. My target again is the CPU on my laptop in this case, right? So the host PC and the target PC are the same thing. They're the same computer. Now I'm going to be starting with no ABS. So let's check it out when there's no anti-lock braking first. And then I'll take you through the different the responses here. So the first button is to connect to a target. Then my the visualization will load. Great. And then I'm ready to drive this. So I'll click on run. So now you see the vehicle going to initial speed. Then the brakes are applied. So as you can see here, as the brakes are applied, then if we look at the slip, the brakes are applied about at the 6 second mark or something, a little bit. So at 6 seconds, the brakes are applied. The slip goes right to 1. When the slip is at 1, that means the car is just, it's skidding the whole way, right? So you saw in the visualization, I'll run it again, but the tires are all locked up, but the car keeps moving, right? And that's depicted in the second scope. So I'll maximize this. The purple line is the angular velocity of your tire. The yellow line is the vehicle speed, represented as angular velocity, right? So your brakes are applied here, your tires lock up, they're at 0 speed, but your vehicle slowly ramps down. And then we calculate, the last parameter that we calculate is the stopping distance. So when does the car stop? So once the brakes are applied, we start calculating the stopping distance, right? And we want to compare basically the stopping distance between ABS on, ABS off. Let me just run it one more time without ABS again. Okay, so it starts going. Brakes are applied now. Brakes, so see the tires are locked up, but the car keeps skidding. So in here we got about 31.7 meter stopping distance. Now, if we activate the ABS, we run the same demo. So now I'm going to run again. The brakes are applied. 6 seconds. So then it'll slow down, but then it starts pulsing a bit. So it didn't do it quite that time, but at the end, I'm just going to increase the desired stiffness a bit. But the stopping distance was less in this case, right? It was 26 meters. So, so with the ABS, it did decrease it a bit by like 4 meters. Let me run it again with a different desired slip. So it goes down, and right there. So at that point here, you can see that the slip, so let's look at this again, right? So the slip, instead of going from 0 to 1, and basically the car, you know, skidding across the pavement the whole way, it starts going down. So the last bit, that's where you see the ABS starting to work, right? So it goes down, then it starts pulsing like that. So that means the brakes, like as you know, right, the ABS, it pumps the brake for you, right? So that pulsing is seen in the second graph here. So the vehicle speed is going down, down, that's the yellow, but then your tire starts pulsing, right? So it starts matching the vehicle speed because because that way it improves the traction. And then you have your stopping distance. So yeah, that's one, like, that is just one example of how you could basically rig up something for your research or for your advanced for your project or whatever, and you can that's pertaining to your application. And you know all the shaft, the radius of each shaft and stuff like that, so you can use a 3D printer or whatever and mount stuff on it. This is in addition to all the different, the belts and the pulleys and inertial loads that we all already offer with the system. So that's all I have for you for today. Yeah, let us know if you have any questions, and I'll hand it back to Tim.